Yeah. Okay. So this is a cup of genuine water, H2O. Okay. Have you guys seen this before? This thing? Okay. Ready? I'm gonna try not to make a big mess. Okay, I'm gonna swing it around. So I'm gonna swing this. Whee! Okay. There you go. So this is a good. It's not even really. I mean, you could think of it as a demonstration of centripetal force, but it's really good. I wanted to just briefly talk about centrifugal force because there's actually a really good comic. You guys know the comic X? It's like XKCD or XCKD.
I think so.
It's like little stick figures.
Like a newspaper type.
It's XKCD. It used to be a really popular like webcomic. I'll read it to you. I know it's small. So the comic says, "How do you like my centrifuge, Mr. Bond?" You guys know who James Bond is, right?
Yeah.
Okay. So this is like the evil villain. This is James Bond. Okay. "How do you like my centrifuge, Mr. Bond? When I throw this lever, you will feel centrifugal force crush every bone in your body." And then Bond says, "You mean centripetal force? There's no such thing as centrifugal force." "A laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simply construct Newton's laws in a rotating system, and you will see a centrifugal force term appear as plain as day." And then the last string he says, "Come now, do you really expect me to do coordinate substitution in my head while strapped to the centrifuge? No, Mr. Bond, I expect you to die." The funny part is just, yes, like he's correct that if you, like you can, I'll show it to you if you look up centrifugal force, so you'll often hear people say, "Oh, centrifugal force is fake. It's a fictitious force," which it depends on. That's kind of correct, kind of not correct. But as you can see, there's a whole bunch of. I mean, you can derive the math. This is what the villain is talking about in that comic. Is you can construct Newton's laws in a rotating reference frame, and then you'll see centrifugal force. But anyway, so I don't want you to get confused for an intro physics class. We're not going to do that. We're not going to construct the laws in a rotating reference frame. We often take a bird's eye view of things. So, but with the cup example, I want to show you that just real quick. Cup. Here's the cup. Here's the water. Here's a little platform keeping it, and it's spinning around. Okay. So from our reference frame, so we're washing it. And what we would say is, well, where does the water want to go if you could want anything?
You're spinning and causing it like they want it to go out.
Yeah, well, it wants to travel. I guess what I'm getting at, I get what you're saying with the gravity thing, but he wants to travel in his direction of velocity. So he wants to go tangentially, right? If all of a sudden the string broke, right? Or if all of a sudden the cup disappeared, just magically, the cup disappeared, the water would fly out that way, right? And then eventually, gravity would cause it to fall in a parabolic curve and all that stuff. But he wants to go that way. So what's keeping him in place? The cup. Okay, the cup exerts a force this way, right? Here's your net force that keeps him in the circular path. Does that make sense? So we call that is centripetal force. But suppose you were a tiny little ant person and you were on your boat in this ocean here. This is you. You're upside down. You get what I'm talking about? It's like a little thought experiment here. Imagine you're in that cup. From your reference frame, from your rotating reference frame, don't you just feel like there's gravity there? Don't you just feel like, I'm just chilling here? You guys have all seen these videos, right? Where like a pilot.
That's the one I showed you.
Yeah. You guys have all seen these, right? There's a million of these videos on the internet.
Their oversized blanket sweatshirt for adults and children will be your best.
That's my.
So you got a pilot, takes his Red Bull, okay, and look, he's doing he's rotating, so the centripetal force, right? keeps the cup in place. But from the reference frame, from the rotating reference frame, there's basically like an artificial gravity that allows him to pour his drink. Okay. Does he do another spin? Oh, he does it again. So he's able to drink his drink while doing a spin.
Actually, going for a loop.
Okay, get the idea. What's kind of neat there is he's able to do it. He's able to get that again from his reference frame. He might call it a centrifugal force. From outside the reference frame, you'd say, "Oh, it's centripetal force." But he's able to. Here's his plane. He's able to do it doing this kind of loop, so he can make a circle like that. But he can also make a circle like that. So remind me here, which one's yaw? Is this yaw?
This is yaw.
This, so he's not yawing. He could yaw around, but then everything would kind of fly away from him inside his reference frame. What's this? Pitch?
Pitch, yeah.
Pitch and then roll? Pitch, roll, and yaw?
Yeah, or bank, whichever.
Yaw.
You could.
I like yaw.
You could yaw playing all the way around though.
You can't?
No,
That's not steezy. You can't just be driving and just yaw it, yaw it around?
You can kick in the. But you can kick the rudder, but like there's a point where it stops. Like you can't.
Damn it,
You can't whip it all the way around.
That's very disappointing.
You can't do donuts.
You could be the first, hey, they used to say, oh, you can't do a loop-de-loop, and then that one guy did it. So, hey, you
Remember that
could be
one
the
guy
first
was?
pilot. On your next flight lesson, say, hey, instructor, watch this. The world's first yaw spin. Yeah. Just Tokyo drifted. Okay, so that leads into this. Bob, number 8. Oh, and I guess I gotta show you the 2001: A Space Odyssey clip. So,
Why do we gotta watch this?
huh?
That's oh, okay. That's just really the model.
So,
How long is the actual movie?
it's like 2:45, I think.
Yeah, I kind of see it.
Oh, yeah.
I'm gonna skip forward. It's kind of a long clip, but anyway, you can see the ship. It's this long ship, and I'm trying to see if they show us the rotating from outside the ship. That'd be kind of because the way they do these shots back in this is 1968, I think.
like a big hamster.
Well, I mean, to make this shot, this is probably a model. Like nowadays, they would do this on a computer. They build it in a computer system, but they used to just make these models by hand and then like zoom in on them and film them. So I don't think we get to see the rotating room from outside the ship. Anyway, that's his ship. So from inside his room, he's in this circular room, and look, he's running around. He's like stretching, but. Oh, anyway. Or I wonder if I put these links to these clips in the YouTube chat, do they show up for posterity? So yeah, like if you watch this movie, if you don't know about the how this might work, you might be kind of confused, like how, first of all, why is the room a circle? That kind of thing. So we'll go over that. How does this work? Copy link. Usually if I put them in, if I comment them myself, they'll show up later. Can anyone confirm that?
I don't know if you like type in the live chat.
It's usually going after.
Oh.
But if you put them in the comment on the video.
Okay. Oh, okay, I'll do that. I would point the computer at the. Oh my God. just showed me this really weird advertisement about underwear. I did not consent to that. Didn't want to see that. Well, I commented them. I'll have to maybe get them later. As you can see from this shot, if you are going to watch this movie, I would recommend not being like in an impatient mood because it's very. It is a slow movie. But like you have to be able. And also, if you don't like classical music, that movie might suck for you because the movie has a lot of shots where it plays like a whole classical movement with like some, something kind of visually nice that tells the story, that kind of pushes the story forward. But anyway, so there's if you're looking for like a really intense action-packed movie, that movie's not for you. So, but it's one of my all-time favorite movies. So anyway, okay, so number 8 on our problem set says, how does this work really? So you put someone in a room. Here's them. And a person has mass, so you can kind of think of them like a little point mass. And the radius of the room is, it says 20 meters. Okay. That room, I don't know, that didn't look like quite 20, that maybe it was like a 10-meter radius, but same principle. Did anyone figure this out and has an answer of how many rotations per minute this needs to make this work? Velocity. So you found a velocity, that's good. Anyone? No? Okay. Okay, well the math is pretty simple because I would say, well, when this guy is on Earth, what does he feel? He feels, gravity pulls him down with mg, and the floor pushes him up with mg. And which one of these vectors is really the culprit as far as what makes him feel the weight? What makes him feel like he's heavy? It's really that. It's the floor. Because if he was a skydiver, right, if he jumped out of a plane or if you put him into a box and threw him out of a plane, either one, and there was no normal force, he would feel weightless. That's why the astronauts in the ISS feel weightless, because they still have that gravity vector pulling them down. There's nothing to push them down. Okay. So anyway, so what has to happen here then is, okay, I guess that this floor must be pushing him up with mg. Now, how big is g if he feels regular, if he feels normal? It's 9.8 meters per second squared. Is everyone okay with that? Okay. So if you did something like, well, so F net needs to be F net equals MA, right? And so the net force has to be mg, and then because he's traveling in a circular path, his acceleration is v squared over r. Does everyone understand that step there? You can also think of it like this. G, so 9.8, has to equal v squared over r. So are there any questions? You sure? Well, everyone said they weren't able to figure it out, so I assumed there'd be questions on how it's set up. No? Okay. So what'd you get for the velocity? Solve this, what do you get? Okay.
14. Yeah.
All right, so now the question is, well, what is that in terms of like rotations per minute? Well, okay, let's look at how far is one rotation. That's true. So one rotation. So one rotation with, what's the formula for this distance? Oh my God.
2 pi r.
2 pi r. Also, that word is called circumference. That's the circumference of his circular path. So his distance traveled then, his 2 pi r, what is that going to be? 2 times pi times r. The r is 20, so 40 pi. Let's get a decimal. Oh, my calculator. It's dying. You can be plugged in. Yep. Crunch that number for us. What do you get?
It's
120.
Point what?
6.
Okay. So one rotation is 125.7 meters. Right? That makes sense? So how are we going to connect this then? So, by the way, can we convert this to how many meters per minute? Eventually I'm trying to get rotations per minute, right? Do I have that? It does say minutes, right? Let's convert this. If you go 14 meters in a second, how many meters do you go in a minute? Multiply it by 60. What is that, times 60? Okay. We okay with that? So when you say it like that, it seems like a lot faster, doesn't it? 840 meters per minute. I mean, 14 meters per second is pretty fast. So he travels, when he's rotating, he must be traveling 840 meters per minute. This number is how many meters there are per rotation. You guys see what to do now? Huh? Divide, yes. So the number of meters per minute divided by the number of meters in each rotation. Does everyone understand why we're dividing? Are there any questions on that? Why it's division? Okay. Okay. And what does that come out to be like? Which actually, you're like, okay, that's not that fast, really. 6 or 7 rotations per minute. That's like not. It's roughly what, a rotation every 10 seconds and every 9 seconds or so. So that's not super duper fast spinning. So we feel okay about that. Okay. All right. Let's look at 1 or 2 more things before we're done for the day. All right, so I want to look at 12. This comes back to this idea. You guys might have some frame of reference for this if you've ever been on a roller coaster. Have you guys never been on a roller coaster? No? That's good. I love roller coasters. Hannah's been exposed. No roller coasters for you, Hannah. Come on, she can't be the only one. Last year, like a third of the class had never been on a roller coaster.
Actually, I haven't. I was thinking
Guys, there's no shame in it. You can admit it. It's not a witch hunt, I promise. Yeah, around here, you gotta drive 5 hours to get to Silverwood, and they've got like, I guess their roller coasters are okay. They only have one good roller coaster, Is it the green one? Oh, the short one. I guess I'm just saying, compared to the Superman one or the Batman one, like ones that you'll see at Six Flags. What's the green one called? Shockwave or something? Aftershock, thank you. Aftershock is like a legit roller coaster. That's what like every roller coaster at a big theme park is gonna be like. Yeah. So, but it's still cool. I mean, I do like Silverwood. It's fun. I guess the wooden ones are kind of fun too. The one that always, I actually can't go on the spinny one anymore. I'm too old now, I guess. Makes me sick. I used to go on those as a kid and love them, but you know what I'm talking about?
Yeah.
You're on a disc and the disc is going along, it's rotating along this axis, but it's also rotating along this axis. It's two different axes. Makes me nauseous. Okay, anyway, here, watch this. So again, this thing spins around. If you were in this thing, if this were a carnival ride, when would you feel, let's say you're sitting, say you were, say it's like a bucket, and you have to be in there like this as it spins around. When would you feel heaviest, do you think? At the bottom or the top? It's the bottom. Now I bring up roller coasters because if you're on a roller coasters will have lots of parts that are effectively circular sections. They might not be technically circles, but like when you're riding through this part on a roller coaster, that's kind of like a circle, right? You see that circular section?
Yeah.
And if you know from experience, at the top of the humps, you feel light. And at the bottom, here's another circular section. Right? At the bottom of the humps, you feel heavy. So I'm going to show you why that is mathematically. Okay, so if you don't know from experience, if you've been on a roller coaster, you know that yes, you feel light here, you feel heavy here. So why is that? Why does that happen? Well, it all has to do with what is the seat? Because where do you get your sensation of weight from, other than your brain? It's their seat pushing your butt, right? Yeah, it's the normal force. So it all comes down to the seat or the track. It's all a chain reaction, right? The track exerts force on the wheels exerts force on the axle exerts force on the chassis exerts force on the seat exerts force on your butt. You get the idea? Ultimately, though, it's the seat pushes on my butt. That's where I feel my weight from. Anyway, so this problem number 12 that we're going to do together illustrates that. So if this ball, this time it's not a person, it's a ball. Just to simplify things. It's a 5 kilogram ball. And at this moment, so the plane of rotation is perpendicular to the ground. So we have a nice side view of this. Side view. So we have to think about gravity now. So this ball is swinging around like I just showed you. And I was showing you this also because you can try it out yourself if you want. It feels heaviest at the bottom. At the top, it feels very light. At the bottom, it feels heavy. You can kind of see my hand. I'm not like really exaggerating that. That's just naturally happening because I have to exert more force to keep it in the path at the bottom. So, okay, vectors. This is actually an easy problem. How big is that vector? 49 newtons. It's mg. So gravity, so the force due to gravity is mg, which would be 49 newtons. Now, how big should I make this tension vector? Should I make it big or small? Big. Because what direction does the net force have to point in order for this thing to maintain a circular path? It has to point inward. So this vector has got to be bigger than that vector. It's got to be significantly bigger. Okay? This is the tension in the string. Most famous formula in physics. F net equals. Oh, by the way, I looked up who invented that formula. It's his name. I'm blanking on his name. It's like Huygens or something, like Christian Huygens in the 1600s. So it was not an ancient Greek guy. I was wrong. But anyway, if you're wondering, I have to look it up. It might not have been Huygens. It might have been something else. Okay, so anyway, F net equals ma. What's the net force according to this force diagram? T minus 49. Here's m. What do we know? This is a mathematical fact. If you are traveling in a circular path, your acceleration has to be v squared over r. Okay? So let's plug in all the numbers that we know. The mass was 5. The v was 6 meters per second. And the radius was 2. So I'm going to have 36 divided by 2 is 18. 18 times 5 is 90. Add the 49. Is that right? I don't know. Use a calculator to check me. Now, how does that number compare? So again, pretend it's not just a mindless ball attached to a string. Imagine it's a person on a roller coaster or something, a ride. How does this number compare to what he is typically used to feeling normal force-wise? It's way bigger, right? It's like almost triple, right? So he'd be like, I feel almost 3 times heavier than usual, right? So 13, I know we're out of time, but at the very minimum, I'd like you to try to knock out a couple problems. At the very minimum, finish 13. 13 is the same exact setup, but the ball's at the top. So the big difference here is that the gravity vector and the tension vector point in the same direction. So when you set it up, it's going to be T plus 49 equals V squared. Oh, I forgot the M, sorry. So that's the only difference. It's the exact same analysis. It's just that now these vectors are working together, so the tension's not going to have to produce so much force, right, to keep this thing in its path. So you're going to find that this tension, the answer to this question is going to be quite a bit less than this one. So if you asked him, how do you feel? He's going to say, I feel very light. I do not feel very heavy or tough. Okay, we're done.